Okay, we're going to go over the homework problem. Before we get started on the homework problem, I want you to pull a few things out. The first thing that I want you to pull out is the chi-square distribution. The next thing that I want you to pull out is just a blank Excel sheet. And I think that's... Oh, and then also the decision-making chart. Okay, so go ahead and pause this for a second and pull that out. Okay, so you should have a chi-squared chart that looks something like this. You can find it on Canvas under the chi-squared tab. And then the decision-making chart, which is right here. Okay, so let's start with the decision-making chart. And let's go through this problem. So we've got this problem right here. Bubba's Fish and Pasta is a chain restaurant along the Gulf Coast of Florida. Bubba is considering adding steak to the menu. Before doing so, he hires a research firm to conduct a study to find out what patrons' favorite meal is while eating. With a level of significance of 0.05, the difference in the number of times each entree is selected due to chance is it due to chance, or should we conclude that the entrees are not equally preferred? Here's the results. So, looking at this, we have Bubba's Fish and Pasta. That is who's doing this research, is a chain of restaurants. He's considering adding steak to the menu. Okay, he hires a research firm to conduct a survey to find out what patrons' favorite meal is. So we've got the patrons' favorite meal. That right there is really... we'll label that... references, review, comment as the dependent variable. Variable is the patron's response. Okay. So what is it dependent on? That's a good question. It is dependent on the options. So there are 4 meal choices. So we're going to comment on that. And this is independent. The meal choices. Then we have the alpha level. Comment. Alpha of 0.05. And what else do we got? Alpha of 0.05, and then sample size of 120. So the next question that I have is, are we comparing, what are we looking at? What is it that we're looking at? So what is it that I want to know? I want to know is the difference in the number of times each entree is selected due to chance, or should we conclude that the entrees are not equally preferred? It literally says that right there. So basically, I want to know is the frequency right here, the difference in these frequencies, I'm comparing these frequencies, is the difference in these frequencies due to chance? Or is everything equally preferred? So am I comparing counts, or am I comparing counts, or am I comparing means? And the answer is I'm comparing counts. So we come right over here in this decision-making chart, and I'm going to click on yellow. In this decision-making chart, we are comparing counts. Next, are the group frequencies expected to be equal? Yes or no? Well, you need to look at the expected frequency. The expected frequency right here is 30. Every group is expected to be 30. Therefore, are the expected frequencies supposed to be equal? And the answer is yes. So if it's yes, then we're going to go through this 6-step process right here and determine the chi-squared information. So we've determined that we are going to be running a chi-squared goodness of fit test, and you can literally follow through this 6-step process right here and go from there. But I'm going to close this now. Don't save. And we're going to keep on going on this chart right here. So we've got the meat categories, count for individual's favorite meal, and now we're getting into the null and alternative hypothesis. So what are the null and alternative hypothesis? Literally, you can come right up here and say, okay, what are the null and alternative hypotheses? Since we're dealing with expected frequencies, I can literally just copy this, Control C, come right down here, and then press Control V, and say, there is no difference between the proportion of, and instead of groups, put adults selecting each entree. And then there is no difference in the proportion of adults selecting each entree. So you notice literally it's the same thing every single time. When you have equal expected frequencies, just put in there, there is an expected difference, there is not an expected difference. Remember, null hypothesis means there is no difference. Alternative hypothesis means there is a difference. Okay, what is the level of significance? Coming right up back up here, 0.05. Okay, and then what is the test statistic? The test statistic we already determined by our fun decision tree. It's chi-squared. What tail is it? Chi-squared is always an upper tail. Remember, looking at this, everything is always going to be an upper tail test. Okay, and with an alpha of 0.05 and the degrees of freedom, with the number of categories minus 1. How many categories are there? There's a total of 1, 2, 3, 4 categories. Therefore, the degrees of freedom is going to be 3. So, there's now 2 ways for you to be able to determine the critical value. Remember, what's the critical value again? The critical value, I'm going to pause it. Okay, so what is the critical value? It's the threshold at which you determine before running anything. That means before you run any sort of tests, the threshold, or that number point, that you determine before running any test, whether you are going to reject or fail to reject the null hypothesis when comparing it to the calculated test statistic, or when comparing the calculated test statistic to the critical value. So you're comparing the calculated test statistic to this critical value, and this critical value is that delineating point. It's that barrier. If it's on this side, you reject the null hypothesis. If it's on this side, you fail to reject the null hypothesis. And so it's that standard, if you will. So there's 2 ways to determine the standard for rejection or fail to reject. The first way is to use a chi-squared chart. And the chi-squared chart is just like the t-chart that we've been using. And I'm going to pull it up right here. And with the t-chart, remember we've got the degrees of freedom, and then we've got the alpha level. So degrees of freedom, alpha level. So we've got the degrees of freedom of 3 and an alpha level of 7, or of 0.05. So therefore, what's the intersection of the two? It's going to be 7.815. 7.815. And so that's what I've got using the chart, 7.815. Now, the other option that you have is in Excel, you can use this formula right here. Okay, so I'm going to copy this formula, and more specifically, it's this formula right here. The probability, I should put, or alpha level. So the probability or alpha level and the degrees of freedom. So that's what we have is the chi-squared. This is the alpha level. This is the degrees of freedom. And so I'm going to copy this. Control C. Go into Excel. Into my fun little scratch sheet here. And I am going to... I've got all this information right here. Chi-squared. There we go. Except I need to get rid of delete. Okay, so the critical value is 7.814727 ... Okay, and this is actually the one for below, and we'll get into that in a little bit. So chi-squared, inverse right tail, probability, degrees of freedom, and this is the critical value. So I'm going to copy this, and I'm going to paste it right here. And then I'm going to go paste as values. And now I've got the critical value according to the Excel formula. Okay, so now what's the decision rule? The decision rule is really easy, and the reason why is because we've only got a right-tailed test, so it's going to be the same thing every single time. The same thing every single time. There's not multiple ways to write this decision rule. There's one way to write it. It's fail to reject the null hypothesis if chi-squared is less than or equal to 7.815, and then fail to reject the null hypothesis if chi-squared is greater than, reject the null hypothesis if chi-squared is greater than 7.815. So in other words, I'm going to move this. There we go. Reject the null hypothesis if chi-squared calculated is greater than 7.815. Fail to reject the null hypothesis if chi-squared calculated is less than this green value right here. And so I picked these up from right here, and I moved them into here and organized them. And you can actually, if you want to know how to edit the shapes, like this shape right here, I'm going to show you something really cool. Double click on it, click edit shape, edit points, and this is under the shape format. And so you can actually edit these points to make it so that it fits inside whatever it is that you're trying to make it fit inside of. And so I'm going to put this right back up here. And so we've got that nice, pretty distribution, and then you're good to go. So that's how you reject, and that's the decision rules for rejecting and failing to reject the null hypothesis. So if the chi-squared calculated is on the right-hand side of here, we're saying that there is a difference, we're saying that the difference between these right here is a legitimate difference. If it's on the left-hand side, we're saying the difference is not a legitimate difference. So let's, now that we've kind of walked through that, I want to go back to this chart right here. Okay, in your chart, when you look at it, you're going to see something that looks a little bit different. Okay, so I'm going to pull up the scratch sheet. You're going to see something that looks like this. Just this. This is all the data that you have. You have no more data than this. 32, 24, so on and so forth. That is your observed frequencies and your expected frequencies. And just from these two pieces of information, you have the ability to derive everything else. So the very first step that we need to take is we need to take the difference between the observed and the expected. And I would highly encourage you, have this chart around. I also have an example for you in our project file. But have this chart around, and then you can do equals 32 minus the expected, and just drag it down. Okay, and we're going to do it without formatting. So now we have the difference scores. Each one of these has a difference score, and then we're going to do equals the difference score and square the difference score. And what are we doing when we square the difference score? We're taking away the negative. Once again, fill without formatting. So we've now taken away the negative, and now that we've taken away the negative, we are now going to find each individual variables, or each individual category's contribution to the chi-square score. So we have equals the squared difference divided by the expected frequency. Okay, equals the squared difference divided by the expected frequency equals the squared difference divided by the expected frequency. Once again, equals the squared difference divided by the expected frequency. So each one of these are the individual contribution to the chi-squared score. Okay, and then in order to get the chi-squared score equals sum, just add them all together. Add all of these together, and so now we have chi-squared. This is chi-squared, which this is a pretty simple. This is a pretty simple problem, and it really is not a complicated math solution at all. You're essentially looking at how much do each of these observed values differ from their expected values, and based on that information, we're generating a score. We're generating a score to say, okay, is there really actually a difference, or is there not a difference? And based on the critical value, that determines whether or not there's a difference. So we're going to take this chi-squared score of 2.2, which you'll notice we've got chi-squared of 2.2 right there, and we are going to put the chi-squared calculated score of 2.2 right here. 2.2, and so the chi-squared calculated score is 2.2, and the probability that we're calculating in just a minute is going to be what is the probability of getting this result of 2.2 or higher, assuming that the null hypothesis is true. Okay. So in order to get the probability of that result, so we've got the calculated value, and we already have the critical value. But in order to find the probability of that result, there are a couple different things that we can do, but really just one that I would suggest. The one that I would suggest is using this Excel formula, chi-squared distribution right tail. In other words, what is the probability of the chi-squared distribution for the right tail? And so we've got x, which is x is your chi-squared value, and 3 is your degrees of freedom. And I should probably put that. X is your chi-square calc value. Okay. So x is your chi-squared calc value. So I'm just going to copy and paste this, Control C, and I'm going to go to my fun little scratch sheet, and I'm going to put Control V, except I'm going to get rid of the 1, which gives us 0.5319 or 0.532. In other words, we have a 0.532 probability of getting a 2.2 or higher. So in other words, there's a 53% chance, assuming that the null hypothesis is true, assuming that there is no difference between all of those categories, there's a 53% chance of us getting the exact result that we got, or something more extreme. Okay. Next, use these images. So we put that all together, and we've determined we're going to now make our decision. What is our decision about rejecting or failing to reject the null hypothesis? In order to do that, we need to compare the calculated value to the critical value. Okay, and what we need to say is we're going to fail to reject the null hypothesis. We're going to fail to reject the null hypothesis because chi-squared calc of 2.2 is less extreme than chi-squared crit of 7.815. Okay. Also, the results are not significant, and there is a 53.19% chance of getting these same results or more extreme, assuming the null hypothesis is true. Okay, so in other words, yeah, there's really not that much to write home about here. All of them are the same, and we'll get to that in just a minute. Next, what is the effect size? Once again, this is a different type of effect size. This right here is Kramer's V effect size. And the way that you calculate Kramer's V is you take chi-squared, and I can do this. Let's see here. Chi-squared calc divided by the total number of observations multiplied by the degrees of freedom. Okay. And then for all of that, you take the square root of this, which I'm going to do this just so it's a little bit easier to see. Take the square root of this formula, which I have it right here. Square root of 2.2, so we have a chi-squared calculated of 2.2. We have 120, is that right? 120? How many observations do we have? We came right up here. We've got 120 observations, and notice that the expected frequency is always going to equal the observed. So we have 120 observations. And then we have 3 degrees of freedom because there's 4 categories, so 4 minus 1. So I'm going to copy this, Control C, and I'm going to go into Excel. And then for the effect size, I'm going to equal square root. This right here is the effect size. Okay, and how do we determine whether or not is a large, small, what type of effect size this is? And the way that we do that is, a second, let me just pull this up. The way that we do that is either by following this table. We've got a table right up here that has the effect sizes, which this is great. However, you notice this table only goes up to 5 degrees of freedom. And so in order to calculate beyond that, there is this formula for saying take 0.1 divided by the square root of the degrees of freedom, and if you have that number, then or smaller, it's going to be a small effect size. It's going to be a small effect size. If you have 0.3 divided by the square root of the degrees of freedom, right around that threshold, it's going to be a medium effect size. And then if you have a 0.5 divided by the square root of the degrees of freedom or larger, it's going to be a large effect size. So let's take a look at what that means. We have 0.1, and let's do this in Excel. Let's see here. We have Word. Okay, so we have 0.1 divided by, so equals 0.1 divided by square root of, what's the degrees of freedom? Degrees of freedom is 3. So 0.1 divided by 3, and so is this right about the same? Well, let's take a look at the medium. Okay, so it's going to be equals 0.3 divided by the square root of 3, the degrees of freedom, and that's 0.1732. And so we can see that our effect size, small, ours, and then medium. And you'll notice that our effect size is very close to the small effect size. So we're going to say that we have, even if we had a result, this would be a small effect size. Okay, and like I said, there is a chart that can do this for you, but it only goes up to 5 degrees of freedom. And so just be aware of that. So that's why I give you this formula, so that way you can calculate it even larger. Okay. So it's a small effect size. Interpret the effect size, and we're going to put the effect size of .07817 is a small effect size. If there were a significant result, the difference between the proportion of the groups would not be noticeable without a larger sample size. Okay, and so that's what that means. So the effect size is a small effect size if it was a significant result, which, do we have a significant result? No. But if there were, the difference between the proportion of the groups would not be noticeable without a larger sample size. Next, interpret your results in a way that you would tell your boss without using stats terms. Okay, so this is how we would write it. The present results do not provide evidence of a difference of preference between the 4 meat choices. Steak would be just as well received as fish, pasta, or chicken. As there's no differences indicated, this difference is not able to be easily observed or detected. Okay, so basically we interpreted effect size. So this is how you should write something like that up. In other words, tell them what they need to know. And when you tell them what they need to know, then they'll be able to make an informed decision. Okay. Hopefully this was beneficial. I will finish the next question in the next lecture.